This video is a sample problem regarding vertical motion near the surface of the Earth. A ball is going to be thrown upward and it reaches 63 meters above the ground at its highest point. And the ball is being thrown by a person, perhaps underhanded, but the ball leaves the person's hand when the ball is 2.2 meters above the ground. We're going to ignore air resistance, and I'm deciding to choose up as the positive direction. So three things here. What is the velocity of the ball at the time the ball left the person's hand in order to achieve 63 meters above the ground? Calculate the velocity of the ball when it hits the ground. The person's not going to catch the ball on the way down. We're going to let the ball travel down to the ground. And calculate the length of time the ball was in the air. This is from the launch time, leaving the hand, until the ball hits the ground. And we're going to use two different methods to calculate this time. So this vertical motion problem, again, it's good to make a little sketch of the situation here. So I've got a simple sketch over here. Ground level at 0 meters. The ball starts at 2.2 meters, reaches 63 meters above the ground. Well, there are four kinematic equations. We do not know the time of travel from the launch up to the highest point. So three of the kinematic equations have that T symbol in them, the time. So we're not going to use those. We're going to use what I'll call the fourth kinematic equation. It only has one unknown for us, only one unknown. The maximum height of the ball, this y value here, is 63. That's the final position in the vertical direction. The initial position when I'm going to start this calculation is at the point of release at the hand. That's 2.2 meters above the ground. The acceleration of gravity is downward, so that's a negative number, minus 9.81 meters per second squared. If your instructor prefers you use 9.8, use that, but do attach negative to it if we've made the choice that up is the positive direction. Very important that you put in a negative number to replace this A symbol, the acceleration. At the top of the motion, the velocity of the ball is 0 for an instant. So I put a 0 in and square that, I get 0. But we want to know this initial velocity at the time, at the instant that the ball leaves the person's hand. What is the velocity in the y direction initially for the time interval we're considering here, the motion interval we're considering here? Well, we put in these numbers, and you should do your own calculation. Pause the video now, pull out your calculator. 2 times minus 9.81 times the quantity of 63 minus 2.2. I came up with 1,192.9, and I'm following through, multiplying the units here, meters in this parentheses, times meters per second squared. We get meters squared per second squared. It's a negative number. I'm going to add this quantity to both sides, so that moves the 1192.9 meters squared per second squared to the left. Now take a square root of this value. When we take a square root, we get 34.5. Meters squared becomes meters, seconds squared becomes seconds. We're taking the square root of everything on the left, and we're a positive here. That's correct. Positive is the upward direction. We're finding the initial velocity at the time of the launch. So it has magnitude of 34.5 meters per second. It has a direction of positive. And let's just see if this is a reasonable number. So converting this to something I'm more familiar with, miles per hour, 1 mile per hour is 0.447 meters per second. So applying this conversion factor, I get a launch speed of 77 miles per hour. Somewhat reasonable. Maybe not for an underhand throw, but maybe for some other arm motion. A professional baseball player throws baseballs at over 100 miles per hour. So this is probably the top end of a reasonable number, but I think it's valid. Put a comment in if you think I made a math error. Now, what's the velocity of the ball when it hits the ground? Well, we can start this at the top of the motion. So now this calculation, why not, the starting location is 63 meters. And we're interested in the velocity when we hit the ground. We want to know this v number. Again, I don't know this time in advance. So I'm choosing, again, the fourth kinematic equation. Acceleration in the y direction is minus 9.81. When the ball lands, this y here is the final position at the end of our time interval, the end of our motion. So that's 0 meters at the instant the ball hits the ground. Again, do the calculations here on your calculator. Pause the video. And 2 times 9.81 times 63, the minus signs produce a positive 1236.1. Take a square root of both sides, and this, on your calculator you'll find positive 35.2 for an answer. Why do I assign a negative? If we're asking velocity, velocity also requires a direction. At the start of this problem, we identified upward as the positive direction. We're on the way down now when the ball hits the ground. Think about the physics, the actual event taking place. The ball is moving downward. It's moving in the negative direction. So I go ahead and attach a minus sign here. Square root will always produce a positive, but I attach a minus sign from knowing the physics of the situation. The speed is 35.2 meters per second. If you remember, if you pause the video and maybe replay it, you'll find that the ball left the hand in the upward direction at 34.5 meters per second. Why is this speed larger when the ball hits the ground than when it was moving upward from the hand? Well, if you recall, the ball started 2.2 meters above the ground. On the way down, this ball continues accelerating towards the ground over this 2.2 meter distance. So we get a little larger number. If the person would have caught the ball 2.2 meters above the ground, what would the speed at the hand be? It would be 34.5 meters per second if we're ignoring air resistance, because we have symmetrical numbers up and down in a problem with no air resistance. But we're moving a little further, accelerating a little further, so we get a little larger number for the speed at the ground, the velocity at the ground. The magnitude of the velocity is the speed. Well, part C, calculate the length of time the ball was in the air. Starting our discussion here from the time the ball leaves the hand until the ball hits the ground. Well, there are really two parts to the motion. There is, that's why I'm going to analyze this in the first method I'm going to use here. There's an up part to the motion to get from the hand to the high point. There's a down part to the motion from the high point down to the ground. Moving upward, the first kinematic equation, the final velocity equals the initial velocity plus the acceleration multiplied by the time. Well, at the top of the motion, our velocity is 0. Again, we're doing this first segment of the motion, moving upward. At the top of the motion, this final velocity is 0. The velocity when we left the hand is plus 34.5 meters per second. Again, we have this negative acceleration because up is the positive direction. Acceleration due to gravity is a negative number. And the t up is what we want to find. So we move the 34.5 meters per second to the left by subtracting this number from both sides. So I've got minus 34.5 divided by minus 9.81, and we get 3.52 seconds. If you also want to check the units, it's seconds. We're dividing by this meters per second squared, so the meters will cancel. One factor of seconds cancels the seconds, and we're left with seconds in the numerator. The time going up is 3.52 seconds. Coming down, what is the final position of the ball when it hits the ground? It's 0. What's the initial position in this part of the motion where we're moving downward? We're starting at the top. That's 63 meters. That's a positive number. There's a negative in the equation. And then 0.5 Now we add the two velocities together. This is the second kinematic equation. So the final velocity plus the initial velocity. The final velocity is downward, so I put a negative number in there, minus 35.2. And the initial velocity at the top of the motion, for an instant the ball is at rest. When you throw a ball upward, if you watch it carefully and then come back down, at the top of the motion, for an instant, the ball is at rest. It's being accelerated, but the velocity is 0 for an instant. Okay, pull out your calculators, pause the video. Minus 63 divided by 0.5 divided by minus 35.2, and I came up with 3.58 seconds. Oh, why is that different? Why is it not 3.52? Well, again, going up, we're starting at the hand. Coming down, we're going all the way down to the ground. So there should be a time difference. If I add the two together, I get the time in the air, 7.1 seconds. Method 2. Now I'm going to do this all in one calculation, where the start of the calculation is the ball leaving the hand. The end of the calculation is when the ball hits the ground. So my third kinematic equation, or your third kinematic equation, can we calculate the displacement here, the y minus y naught? Well, in this situation, the final y is 0. We're at the ground. The initial y is 2.2 meters off the ground. That's where the ball left the hand of the person. That was the position at the start of this time interval calculation. Our velocity when the ball leaves the hand, 34.5 meters per second upward. T air is unknown, the time in the air. And then the third kinematic equation has 0.5 times the acceleration times the time squared, times the time squared. So we get, again, minus 9.81 for the acceleration in the y direction. The numbers I put in here are all y numbers, the vertical numbers, 34.5 meters per second upward. The y position when we end, the y position when we start. It is very important to never put an x-type number, a horizontal number, in a vertical calculation. Again, pause, put in these numbers and do the calculation on your own calculator, and you'll find 4.905 is the coefficient of t squared. It's 0.5 times minus 9.81, minus, I should say, minus 4.905 is the coefficient of t squared. Now, I prefer in quadratic equations to have the coefficient of the squared variable as a positive. So I'm going to add 4.905 times t squared to both sides. I'm going to subtract 34.5 times time to both sides, and I get this quadratic equation. How do you solve quadratic equations? Well, you could try to factor this if you want, but it's simpler here just to go to the quadratic formula. The value of the unknown, there's going to be two values, is we take a minus sign, put a minus sign in front of the coefficient of this middle variable, t to the first power. So it's going to be a minus b, plus or minus square root of b squared. Again, b is the coefficient of this first powered variable. Minus 4 times a is the coefficient of the squared variable, that term. And then c is the constant in the problem here. And then divide, after you do this calculation, you're going to be dividing by 2 times a. Something to be cautious of here, careful of. What is the value of c? C is a negative number. When you do this calculation, make sure you're multiplying by minus 2.2 in the process. So the steps I came up with, so minus b, I get minus a minus 34.5. Again, b itself is a negative quantity. Plus or minus the square root. And you should pause and do this calculation. B squared minus 4ac, the discriminant. I came up with 1233.37. And then again, pause the video, do the square root on your calculator, and you'll get a positive number. There are going to be two solutions. One time we take a plus, the result of the square root value. Another time we're going to do a negative. When I use the plus sign, this is also a plus. So we're going to have some positive quantity divided by 9.81. I came up with 7.1 seconds. If you use the negative sign here, so this is plus 34.5, and then a negative, the result of the square root of 1233.37, and I came up with minus 0.06 seconds. We start the time when the ball leaves the hand. So we're looking for some positive time. A negative time would be in the past, so to speak. So we just disregard that negative solution. So I come up with this quadratic equation giving us 7.1 seconds. I'm going to flip back to the previous page. 7.1 seconds was the result, doing the calculation in two steps, an up part and a down part. I get 7.1 seconds for this, doing the calculation one time. A little more complicated calculation, but there's only one of them. And so we have agreement on those two. So that's vertical motion. Very important to keep the numbers y's and x's separate if you're doing projectile motion. I have lots of YouTube videos with sample problems worked out and lectures and brief lectures for physics and astronomy. Go to gpclements.com. Everything there is free. It's not available for resale. Not allowed to do that, but it's free. You don't register. You don't give me your email address. You don't give me your name. You don't give me any money. You just use the material and hopefully learn some more physics. And the website here does not put cookies onto your computer. So hope you're working sample problems. Ask your instructor if you have questions.